Dr. O here, and in this video we're going over the gas laws according to our buddies Robert Boyle, Jacques Charles, and Amedeo Avogadro. Each of these gas laws deals with only two changing variables in a given scenario. These variables will either be volume and pressure, volume and temperature, or volume and moles. In any problem, you'll have an initial set of variables and a final set of variables, and your task is to be able to solve for one of those variables. So let's have a look. So here on this slide, first of all, before we read our problem, we have Boyle's law, and Boyle's law basically says that you have an initial volume and pressure that are equal to the final volume and pressure, where your temperature and your moles are being held at a constant. So if we introduce a problem, we can see how it is we're expected to solve for one of these unknowns. So our problem reads that an air bubble forms at the bottom of a pond where the pressure comes in at 2.50 atmospheres. At this pressure, the air bubble has a volume of 0.31 liters. The bubble rises to the surface where a cold front has created increased atmospheric pressure, which now measures at 1.50 atmospheres. What is the volume of the bubble at the pond's surface? And it states clearly here that we are to assume that temperature and moles are held constant. So let's take a moment and see what we're given. First, we're given the pressure at the bottom of the pond where the air bubble is forming, and that comes in at 2.50 atmospheres. And we're also given the volume of the bubble, which is 0.31 liters. The bubble rises from the bottom of the pond to the surface, and at the surface the bubble now encounters a new pressure of 1.50 atmospheres, and we are being asked to find the volume of that bubble at the pond surface with this new pressure acting on it. So because we're given the variables of volume and pressure, where the temperature and moles are being held constant, we know that we're going to be using Boyle's law. We also have to accurately identify our variables in order to set the equation up to solve for the unknown. Our variables for Boyle's law are going to be the initial volume, which we write as V with the subscript I. I stands for initial. And then we have initial pressure, which we write as a capital P with a subscript I. And those are going to be equal to our final volume, which we write with a capital V with a subscript F, F standing for final. And then final pressure, which we write with a capital P, also with that subscript F for final. So let's start by identifying our variables. And we have them listed here. So our initial volume, we can fill that in because that comes in at 0.31 liters. The initial pressure, which is PI, is 2.50 atmospheres. And the final pressure, which is PF, is 1.5 atmospheres. And our unknown variable, which is the one that we're solving for, is the final volume. So let's take these values and plug them into our formula, and our problem now reads that 0.31 liters times 2.50 atmospheres is equal to our final volume, VF, times 1.5 atmospheres. Now our unknown is the final volume, VF, and what you want to do is you want to isolate that. We want to move all the numbers to one side of the equation and leave that unknown by itself on the other side of the equation. And in order to do that, I'm going to divide both sides of this equation by 1.5 atmospheres. And when I divide the right side of the equation by 1.5 atmospheres, it will cancel out on this side. But on the left side of the equation, it will appear in the denominator because remember, I'm dividing by this number. So let's do that now. Now, when I have a problem that's written as a fraction, it's a good idea to check to see if you have any terms that appear both in the denominator and the numerator, because if you do, you can cross those terms out. And in this case, we have the units of atmosphere that appear in both the denominator and the numerator, so we can cancel those two out. Now we're left with the unit of liter. And now's a good time to ask yourself, there's our liter. Now's a good time to ask yourself, does this unit help me answer the question that I'm being asked? And if we go back up to the top, we can see that the question we're being asked is, what is the volume? So in fact, there's our amount that we're being asked to answer. And does liter, the unit of liter, help us answer the question about volume? Well, liter is a measure of volume, so yes, it does. So double checking your units at this point is a good way to make sure you've set the problem up properly. If we didn't have a volume measurement at this point, we would need to rework the problem. Otherwise, we wouldn't be able to answer that question, what is the volume? So now we're at a point where we can simply do the math, and we're going to multiply the numbers on top, which is 0.31 liters times 2.50, and we're going to divide by what's on the bottom, which is 1.5, and we get 0.51667 liters, which is equal to our final volume. And if we take a look back through our given values, we can see that the value for the fewest significant figures is the initial volume, which has 2 significant figures. So our answer must also have 2 significant figures, which makes our final answer 0.52 liters. Now, in our last problem, we solved for the final volume. Let's see what our new problem is going to ask us to do. So, having nothing better to do, you decide to blow up a balloon and take it down to the deepest part of your neighbor's swimming pool. At the surface, the air pressure is 0.75 atmospheres, and the balloon has a volume of 2.25 liters. At the deepest part of the pool, the balloon has a volume of 0.85 liters. What is the pressure at the pool's deepest part? Again, assuming that in this scenario, the temperature and the moles are being held at a constant. So in this scenario, we blow up a balloon at the pool's surface and then take it down to the bottom of the pool and see what happens. Our initial values of pressure and volume are going to appear at the surface, and our final pressure and volume will be at the pool's bottom. So that's the change that's happening in this scenario. First, we're given the pressure at the pool's surface, and that comes in at 0.75 atmospheres. And we're also given the balloon's volume at the surface, which is 2.25 liters. At the bottom of the pool, the balloon's new volume comes in at 0.85 liters, and we are being asked to find the pressure on the balloon at the bottom of the pool. So we're going to be using Boyle's law for this. Now, because we're given variables of volume and pressure, where temperature and moles are of gas are being held constant, we know that that's Boyle's law. We also have to accurately identify our variables in order to set up the equation to solve for our unknown. Our variables for Boyle's law are going to be initial volume, initial pressure, final volume, and final pressure. So let's begin by identifying our variables. And our initial volume is going to come in at 2.25 liters. Our initial pressure is 0.75 atmospheres. The final volume is 0.85 liters, and our unknown is the final pressure. This is what we're going to be solving for. So if we take our values and we plug them into our formula, our problem now reads 2.25 liters times 0.75 atmospheres is equal to 0.85 liters times our final pressure. Now our unknown is final pressure, and we want to isolate that. We want to move all the numbers to one side of the equation and leave that unknown by itself on the other side of the equation. In order to do this, I'm going to divide both sides of this equation by 0.85 liters. When I divide the right side of the equation by 0.85 liters, it will cancel out on this side, but on the left side of the equation, it will appear in the denominator because we're dividing. So let's do that now. Now, when I have a problem that's written as a fraction, it's a good idea to check to see if you have any terms that appear in both the denominator and the numerator, because if you do, you can cross those terms right out. And in this scenario, we have the units of liter that appear both in the denominator and the numerator, so we can cancel both of these out. And now we're left with the unit of atmosphere. And now's a good time to ask yourself, does this unit help me answer the question that I'm being asked? Does it help answer the question of what is the pressure? And let's see, atmosphere is a measure of pressure, so yeah, it does. Double checking your units at this point is a good way to make sure you've set the problem up correctly. If we didn't have a pressure measurement at this point, you would need to rework the problem. Otherwise, we won't be able to answer the question that we're being asked. So now at this point, we can just do the math, and we're going to multiply the numbers on top, which are 2.25 times 0.75 atmospheres, and divide by what's on the bottom, which is 0.85. And we get 1.9853 atmospheres being equal to our final pressure. And if we take a look back through our given values, we see that the value with the fewest sig figs is the initial pressure, which has, it has two, let's see, it does have two significant figures. I had to double check my own work. So our final answer must also have only two significant figures, which makes our final answer 2.0 atmospheres as the final pressure. Now, to review, what we've done with these last two problems is we first of all identified that we're using Boyle's law. That is, we have a problem where we have the changing variables of pressure and volume. And then second, we identified our known variables and which one is the unknown variable. And then third, we plugged those variables into our equation. Fourth, we isolated the unknown. Step number 5, we crossed out repeating terms and used this step to double check that the remaining units helped us answer the question we were being asked. And then sixth and lastly, we did the math being mindful of significant figures. And those are the steps that we're going to go through when looking at the other two laws as well. Here we have Charles's law, which states that the initial volume and temperature are equal to the final volume and temperature, where temperature is in Kelvin, and the pressure and moles of gas are held constant. So if we introduce a problem, we can see how we're expected to solve for one of these variables. And our problem reads, a plastic bag in the cargo hold of an aircraft undergoes a temperature change from 53 degrees Celsius to 10.2 degrees Celsius between takeoff and when the aircraft reaches flying altitude. If its final volume is 20.4 liters, what was the initial volume of that plastic bag? And again, it states we assume that pressure and moles are held constant. So let's take a moment and see what we're given. First, we're given the initial and the final temperatures, and we're also given the final volume, and we're being asked to find the initial volume. Now, because we're given the variables of volume and temperature, where pressure and moles are held constant, we know we're going to use Charles's law. Now, we also have to accurately identify our variables in order to set the equation up to solve for the unknown. And the variables for Charles's law are initial volume over initial temperature, and we write that as a capital V with a subscript I standing for initial, over a capital T with a subscript I. And that's equal to our final volume over final temperature, which we write as a capital V with a subscript F, F standing for final, and that's over a capital T with a subscript F as well. So let's begin identifying our variables. Our initial temperature is 53 degrees Celsius, and our final temperature is 10.2 degrees Celsius. Our final volume is 20.4 liters, and we have an unknown coming in as that initial volume. Now, before we plug in our numbers into our formula, we have to convert the temperatures into kelvins. And the good news is that converting from Celsius to Kelvin is really easy. All you have to do is add 273.15 to your Celsius measurement, and you now have kelvins. So let's do that now. So here we've converted our initial and our final temperatures into Kelvin, and these are going to be the values that we use to plug into our formula. So now that we've dealt with the temperature conversions, let's plug in our values. And our problem now reads that our initial volume over our initial temperature, which is 326.15 Kelvin, is equal to 20.4 liters over 283.35 Kelvin. Now our unknown is the initial volume, and we want to isolate that. We want to move all the numbers to one side of the equation and leave that unknown by itself on the other side of the equation. Now in this equation, if we multiply both sides by 326.15 Kelvin, we can eliminate this from the left side of the equation, and it's going to appear on the right side of the equation. And because we're multiplying it in order to get it out of the denominator on the left, our number is now going to appear on the right side in the numerator. So let's do that little procedure right now. Now when I have a problem that's written as a fraction, it's a good idea to check to see if you have any terms that appear in both the denominator and the numerator, because if you do, you can cross those terms out. And in this case, we have the units of Kelvin that appear both in the denominator and the numerator. So we can cross those right out. And that's going to leave us with the only unit there, which is the liter. And now's a good time to ask yourself, does this unit help me answer the question that I'm being asked? Does it help me answer the question, what was the initial volume? Well, liter is a measure of volume, so yeah, it does. Double checking your units at this point is a good way to make sure you set the problem up correctly. Otherwise, you aren't answering the question being asked. So now at this point, we can do the math, and we're going to multiply the numbers on top, which are 20.4 liters times 326.15, and we're going to divide by what's on the bottom, which is 283.35, and we get 23.48142 liters. If we take a look back through our given values, we see that all of our values have three significant figures. So our answer, our final answer, must also have three significant figures, and that makes our final answer 23.5 liters. All right, let's work another Charles's Law problem. So here we are given the problem that we have a container of carbon dioxide gas that has an initial volume of 13.0 liters and a temperature of 22.0 degrees Celsius. And we're supposed to calculate the temperature if the volume of our container is changed to 17.0 liters. And we're supposed to give our answer in degrees Celsius and also assume that pressure and moles are held constant. So let's take a moment and see what it is that we're given. So first of all, we're given that we have an initial volume of 13.0 liters, and we're also given an initial temperature of 22.0 degrees Celsius. The volume of our container mysteriously changes to 17.0 liters, and we're being asked to find what the new temperature is now that the volume has been altered. Now, because we're given the variables of volume and temperature, where pressure and moles are held constant, we know we're going to be using Charles's law. We also have to accurately identify our variables in order to set the equation up to solve for the unknown. And our variables for Charles's law are initial volume, which we write with V and the subscript I, initial temperature, which we write with a capital T and a subscript I, final volume, which we write with a capital V and a subscript F, and final temperature, which we write with a capital T, also with a subscript F. And in Charles's law, our volume is over temperature on both sides. So let's start by identifying our variables. And our initial volume comes in at 13.0 liters. Our initial temperature is 22.0 degrees Celsius. Our final volume is 17.0 liters, and the unknown variable is our final temperature reading, which we need to record in degrees Celsius. Now, before we plug in our variables, the first thing we have to do is convert our temperature to kelvins. And that's a very easy process. All you have to do is add 273.15 to your Celsius measurement, and you have kelvins. So let's do that right now. So we've taken our initial temperature reading, which is 22.0 degrees Celsius, add 273.15, and we end up with 295.15 kelvins. And now that we've dealt with that temperature conversion, let's plug in the values into our formula. And our problem now reads that we have 13.0 liters over 295.15 kelvins is going to be equal to 17.0 liters over our final temperature, our unknown. Now our unknown is the final temperature, and we want to isolate that. We want to move all of the numbers to one side of the equation and leave that unknown by itself on the other side of the equation. We now have a problem for solving for TF, our final temperature. But this is in the denominator, and this seems to pose a problem for students. Now the process I'm going to use to solve this is actually algebraically sound, but the way I'm going to do it is going to save you a lot of steps. It's going to avoid doing a lot of additional algebra. What I'm going to do is simply to flip the entire equation. And through the magic of PowerPoint, there it is. Now you can work this out for yourself. This is algebraically sound. You are allowed to do this maneuver, but remember, if you're going to flip one side, you have to flip the other one. So I've turned the entire equation upside down. So from one to the other, I took what was in the denominator on both sides, put it in the numerator, and then I took what was on the numerator of both sides and put it in the denominator. So now it looks like this. This is easier to deal with, having that unknown in the numerator, and this little maneuver allows you to do that. So now at this point, I can simply multiply both sides of the equation by 17.0 liters, and this will eliminate it from the right side of our equation, and it will appear on the left side of the equation in the numerator, because remember, we're multiplying in order to eliminate it from one side. So let's do that now. So the problem looks like this. Yes, it is noon. All right, now I have a problem that is written as a fraction, and it's a good idea to check to see if you have any terms that appear in both the denominator and the numerator, because if you do, you can cross those out. And in this case, we have the units of liter that appear in both the denominator and the numerator, so we can eliminate both of those, and that leaves us with the unit of Kelvin. And now is also a good time to ask yourself, does this unit, this one remaining unit, help me answer the question that I'm being asked? Does it help me answer the question, what is the temperature now that volume has changed? Well, Kelvin is a measure of temperature, so yeah, it does. Double checking your units at this point is a good way to make sure you've set the problem up correctly. If we didn't have a temperature measurement at this point, we would need to rework the problem. Otherwise, we wouldn't be able to answer the question that we're being asked. So now we can simply do the math. And we're going to multiply 17.0 by 295.15 Kelvin, and we're going to divide by what's on the bottom, which is 13.0, and we get 385.96 Kelvin is equal to our temperature, final temperature, yes. Now our problem is asking not only for the final temperature, but specifically to give that temperature in Celsius. So we must convert this answer from Kelvin into Celsius. Now when we converted from Celsius to Kelvin, we added 273.15 to the Celsius reading. To go the other way, that is to convert from Kelvin to Celsius, we're going to do just the opposite, which means we're going to subtract 273.15 from our Kelvin measurement. So let's do that now. There it is. And our answer becomes 110.8154 degrees Celsius. Now, if we take a look back through our given values, we see that all of our values have 3 significant figures, so our answer must also have 3 significant figures. And since I'm at the bottom of the slide and don't have any room to add anything else, I'm going to put my answer next to the variable, which is t sub f, and our final answer is 111 degrees Celsius. Now to review what we've done with these two problems, we first identified that we were using Charles's law. That is, we had a problem where the changing variables were temperature and volume. And then second, we identified our known variables as well as the unknown variable. Third, we plugged in those variables into our equation. Fourth, we isolated the unknown. Fifth, we crossed out repeating terms and used this step to double check that the remaining units helped us answer the question we were being asked. And sixth, we did the math being mindful of significant figures. Here we have Avogadro's law, which states that initial volume over moles are equal to final volume over moles, where temperature and pressure of gas are held constant. So if we introduce a problem, we can see how we're expected to solve for one of the unknown variables with this formula. And our problem reads that we have a patient with emphysema. And this patient has lungs that have a volume of 3.85 liters that fill with 0.45 moles of air when the patient is inhaling. Now, when the patient exhales, the lung volume decreases to 2.30 liters, and we're being asked how many moles of gas remain in the patient's lung after exhalation. So let's take a moment and see what we're given. First, we're given a volume of 385 liters when the patient has fully inhaled, and we're also given the moles of air in the lungs at that point, which is 0.45 mole. Now, when the patient exhales, the lung volume has changed to 2.30 liters, and we're being asked to find out the moles of air in the lungs at this point, at the end of exhalation. So because we're given the variables of volume and moles, where temperature and pressure are held constant, we know that we're using Avogadro's laws. Now our variables for Avogadro's law are initial volume, which we write as capital V with subscript I, over initial moles, which we write as little n with subscript I. And that's going to be equal to our final volume, which we write with capital letter V with a subscript F, and that's going to be over little n with a subscript F. So now we have to begin identifying our variables, and our initial volume is 3.85 liters. Our initial moles are 0.45 mole. Our final volume is 2.30 liters, and the thing that we don't know are the final moles, and that's what we're solving for. So let's plug in these values into our formula, and our problem now reads 3.85 liters over 0.45 moles will be equal to 2.30 liters over our unknown value, which is our final moles. Now our unknown is the final moles, the NF, and we want to isolate that. We want to move all the numbers to one side of the equation and leave that unknown NF by itself. Now this problem is just like the previous problem where our unknown is in the denominator. So the trick that we can use is to flip both sides of the equation, bring what's in the denominator into the numerator, take what's in the numerator and put it in the denominator. That is algebraically sound. If you need a video proving that, I can do that, or you can just ask me in my classroom if you happen to be a student. But we're going to do that right now, so we're going to flip everything. And our equation now looks like this. Now, in order to solve for the unknown, which is now in the numerator, I'm going to multiply both sides of this equation, our new equation, by 2.30 liters. Now by doing that, I get to cancel out what's in the denominator on the right-hand side, and then 2.30 liters will appear in the numerator on the left-hand side, because now we're multiplying to eliminate what's in the denominator on the right-hand side. So let's do that now. All right. And now we have a problem where we have a number that's a fraction. And it's a good idea at this point to check to see if you have any terms that appear both in the denominator and the numerator, because if you do, you can cross those terms out. And in this case, we have the units of liter that appear in both the denominator and the numerator, so we're going to cross both of those out. And that leaves us with the units of moles. And now's a good time to ask yourself, does this unit help me answer the question that I'm being asked? Does it help me answer the question, how many moles of gas remain in the lungs? Well, mole is a measure of mole, so yeah, it does. Double checking your units at this point is a good way to make sure you've set the problem up correctly. If we didn't have a mole unit at this point, we would need to rework the problem. Otherwise, we wouldn't be able to answer the question, how many moles you got at the end of this thing? So now we can simply do the math, and we're going to multiply 2.30 by 0.45 mole and divide it by what's on the bottom, which is 3.85, and we get 0.26883 mole as our final moles. And if we take a look back through our given values, we can see that the value with the fewest sig figs is the initial mole, which has 2 significant figures, which means our answer must have 2 significant figures, which makes our final answer 2.7 moles. To review, what we've done with this problem is what we've done with all the problems that we've worked. First, we identify which law that we're using, and in this case it was Avogadro's law, and that is that we had a problem with the changing variables of volume and moles. Second, we identified our known variables and the unknown variable. Third, we plugged in those variables into our equation, into our formula. And fourth, we isolated the unknown using a little algebraic magic. Fifth, we crossed out repeating terms and used this step to double check that the remaining units helped us answer the question we were being asked. And sixth, we did the math, being mindful of significant figures. Now it's your turn to work some problems. On the slides that follow, there won't be any narrative. The video will advance from step to step in the problem-solving sequence, which is the same sequence I've done with all the previous problems. There are pauses in between each step to allow you time to follow the process, and of course you can always pause the video and work the problems on your own. So, here you go.